or whatever, and you think, whew, that's good, that was, 100 meters away from me, how lucky am I? Except that if the ground's wet, the currents can travel through the ground and get you through your shoes. So rubber shoes are your friend,
Thank you.
I saw something back here. Yeah.
Yeah, as far as your question about pollen, the study how they went and looked at after thunderstorms, the pollen, at least the grass pollen, they looked at tend to fracture and break up into smaller pieces. It thought they psychology, the current, whether it's the wind.
I don't know.
Fractured pollen.
Yeah, I don't know. That's interesting. There's so many hands.
Comment and a question. There's a story about Robert Oppenheimer, who was at a picnic out in the Pecos Mountains, and there was a storm. And his companion noticed that Oppenheimer's hair started to raise up like that, but then it went back down again. I mean, that could have changed history. The question is, there's this weird spooky phenomenon called ball lightning, where the current channels kind of come together and spook around and can travel around and everything.
So I've looked ball lightning up, and there's been many stories going back hundreds of years. People say ball lightning. Some people, pictures again on Wiki, there's these engravings from the 1700s where it looks like something comes in somebody's chimney and it's this glowing orb. But nobody's ever caught it on film. But nobody had ever caught sprites on film either. So if it's a super rare phenomenon, it's super hard to be in the right place at the right time. So I honestly, I don't know anything about it because it's never been recorded.
I think I saw it about a month ago over the Davis to the northwest. I was just going to ask you and thank you about the streamers. Because I saw this lightning, and then all of a sudden there was this hot pink ball.
Uh-huh.
Where did that come from? Is it the beginning of a forest fire,
Yeah.
But no, it was a perfectly round, hot pink orb, and then that was it.
Yeah, we don't know anything about it because we haven't measured it. We can't seem to catch it. But there are eyewitness accounts of things like this going back hundreds of years.
There's interest in that in nuclear fusion.
So if you can catch one,
Well,
you will be, yeah.
He's talking about that in cattle drive.
Yeah.
What's the energy spectrum of the gamma rays and X-rays, and how do you use the Monte Carlo?
So honestly, I don't look at the X-rays or the gamma rays from lightning. It's a different set. It's the Ricci satellite that's been looking at the gamma ray flashes, so I really don't know the spectrum of them. They're not super energetic. They're not, it's not a terribly hard spectrum because they don't get out from very low in the atmosphere. They're pretty high in the atmosphere. My Monte Carlo stuff is, for example, I did optical radiative transfer modeling. So how does the light get out of the cloud? So the lightning is pretty fast. Why does the light signature look so long? On our comparatively long, and it's because it's scattered in the clouds. That's something I should mention. Lightning, it looks like it flickers. That's because once that connection is made anywhere between two layers in the cloud or to the ground or whatever, now there's this great big superhighway, and the charge tends to dump and then recover for a minute, and then it dumps again down the same, because it's already there, the path is already there, and slowly the path decays and it goes away. And I think some of the records for this multiplicity of strikes is like up to 20 strikes down the same channel, lasting many milliseconds. It just keeps dumping charge and dumping it again.
Yeah, you covered a lot of ground, and just about every one of them had questions on it. The only one that's kind of stuck in my mind, I don't know what the question was. What was a quick review on the neuromagnetic events?
The narrow bipolar events?
Yeah.
So that description just says that when they happen, when lightning hits the ground, so a cloud-to-ground event, the electric field deviates quickly, and then it sort of recovers, and it's a comparatively slow process, hundreds of microseconds, tens of microseconds. A narrow bipolar event lasts like 1 microsecond or less, and it's just this huge, it's incredibly powerful VHF radiation, the most powerful thing we've seen. It's fast. It comes before the rest of a flash, so it's always like the first thing in a flash, and it has no light associated with it.
Okay, all right, so it's kind of like the peculiar features that it's a narrow bandwidth thing, it's just a a narrow radio wave, but no.
It's a fast thing, super fast.
Whereas most lightning is very spread spectrum.
Well, it's still spread spectrum, but it's narrow in time. So that narrow refers to how narrow on the time series. The frequency spectrum, it's still wideband.
Oh, it is.
Mhm.
Because you said it was VHF.
Yeah, so all lightning is wideband up to, say, it's like from DC to like maybe 150 megahertz
I
kind of
think
thing.
I was associated so much with broadcast and HF.
Yeah, so
Because,
it's,
you know, the communications used to be so dependent on HF, and
yeah.
I'm not certain.
It goes through HF. I use the VHF as the example because that's what I observed from orbit.
I have two quick but unrelated questions. The first one is, like, we were looking at back over our deck the other day, and two thunder clouds over the Sangres. And it would appear as if there's lightning over here, and then all of a sudden there's lightning over here. Can you get triggering of lightning in another cloud from a first, or is that just serendipitous that they're happening at the same time? It's like both giant thunderheads will light up at the same time, seemingly correlated.
Well, like I said, conceivably, you can't see all the connections, and you certainly can't see the charge layers.
Okay.
They might be the same complex of charge layers. You can get these huge storm complexes called mesoscale storm complexes that go, for miles. And so the charge layers are like these huge pancakes of charge, and stuff is related, over Norman, Oklahoma, and,
Okay.
way the hell away. So they could be related. So yes, maybe, I don't know.
The second question is, and this one's a flyer, gas giants, are there any analogs of lightning in atmospheres other than Earth?
At least Jupiter, I think Venus. So yes, there is. It's been observed.
Same mechanisms, colors are different?
We don't even know the mechanism on Earth. I have no idea the mechanism on
Are
Jupiter.
the colors different?
I don't know. I don't know how carefully it's been studied. We know it happens.
Okay.
So
So what's the driving force of getting lightning from a cloud that's like 20,000 feet above the earth, all the way down to the ground?
I'm sorry, I missed the
What's the
beginning.
driving force to get to the ground? It's a long distance, right?
It is.
And so how does the electron 20,000 feet up know that there's a ground down on the earth?
I don't know. I mean, if the electric field was super big, okay, it would just be like a great big capacitor, and you finally got a huge ability to create an arc, and it would be as simple as that. But the electric field is not that big. And I think I'm grateful because I don't want the whole cloud discharging to ground. Every time there was a thunderstorm, we'd be killed. So I don't know. And so I think if it's not cosmic rays making some kind of preferred channel and then letting it suddenly discharge along that channel. Another theory is that you get these tiny little regions of enhanced electric field. So a little region gets a super strong electric field, you get a little discharge. And somehow all the charge migrates to the tip of that region, and you get another super enhancement of electric field, and you get another little discharge. But we're never able to find, I can't get my balloons, to go right up through that while it's happening. And it just, we don't know exactly how it's happening. It is, I don't know. That's the answer.
How much of this can you simulate in the lab?
Not much, because you can induce something in the lab. You can induce a great big spark, but does that have any resemblance to what's happening in clouds? I don't know. And you can't get it as big as this, so I don't know. I saw a whole bunch of hands back there.
So you mentioned that you're seeing gamma ray events. Are these observed in high atmosphere because you've got satellites that can actually get and detect the opacity of the atmosphere, or do you have any reason to believe that you might produce them at ground levels?
I think they're happening in the high atmosphere because if they're happening near the ground, we aren't seeing it because we aren't close enough. The gamma rays get absorbed. But there were some experiments with triggered lightning where you're deliberately triggering the lightning, and so you put your sensors right there because lightning's going to strike right there. And that's where they saw some of these the X-rays coming off the tip, and they think they saw some gamma rays as well. But the stuff that's been observed just in nature that wasn't triggered is from satellites, and they do think that what they're seeing is gamma rays that occur high in the atmosphere, and that's why the gamma rays get out. It has not been observed by your average ground-based array that's many kilometers away from a given event. And Yeah, so the ones they see are from high in the atmosphere, but that doesn't necessarily mean they aren't happening lower.
Are you talking about the gamma rays from the lightning or
Yeah.
the gamma rays triggering?
Gamma rays from the lightning. We've tried to do studies looking at, trying to do statistical studies of cosmic ray impact rates over parts of, quiet parts of the Earth and look to see if lightning is enhanced or anything. And we just don't have sufficient data to see that, so.
Just one quick question, then maybe a little more complex. So the quick one is, have you seen any differences between volcanic or lightning that's being caused by dust storms versus thunderstorms?
So there's a woman at the lab right now who studies volcanic lightning. I should say that over thunderstorms and over volcanoes, a lot of lightning is seen, totally typical. And it does seem to have to do with the charged ash. You get a big updraft over a forest fire, and you've got charged ash. So you've got essentially all the elements necessary to create lightning, and we see it. And the same thing is going on over a volcano. You've got a big lofting of charged ash. So she's studying that, and what they see is there's two kinds of things going on. There's lightning that looks for all the world like any other lightning that you'd see. And then there's also these fans, these VHF fans. There's a specific signature in the radio waves that it's like a wideband pulse that then seems to ring as it decays. And that's sort of unique. We don't see that in storms. And I don't know about over forest fires. I haven't seen any lightning data from over forest fires.
I thought that was the easy question.
Okay.
There seems to be a lot of utilization these days of lightning predictors or detectors for sporting fields and a lot of other things. How effective are those systems, and would you put your kids in the field?
So I think that you could definitely use weather radar to predict when the conditions for lightning are good.
But it kind of depends on which kid, too.
Yeah, what she said. So you can kind of predict when the conditions are right, but predicting any actual lightning strike is not going to happen. And in fact, I saw a talk many years ago where somebody did the statistics on people killed by lightning and how long after like the first report of thunder was it. So, if somebody reports thunder and 5 minutes later you're killed by lightning, you didn't have a sporting chance to get off the field, right? But if it's, an hour later and you've been standing there in a thunderstorm, you kind of brought that on yourself. But there were still people, too, that were killed by lightning before any reports of anything.
Right.
So it's not clear to me how well we can predict that.
So, something I've heard about is positron light. Can you say anything about that? Or?
I can say that signatures of positrons have been detected above lightning. But beyond that, I don't really know anything. Sorry.
So, from a satellite, what's the difference between a nuclear blast and a lightning storm?
One is really a bummer. And
If you're using one to calibrate your instruments, you got to be able to separate it out also.
So an electromagnetic pulse, which is what comes off of a nuclear bomb, is the same kind of mechanism. You have a big release of gamma rays that cause electrons that cause a fast burst of radio waves. It's the same kind of mechanism. And there are differences that I can't discuss. And the light signature is different too, because it's a totally different mechanism for the light. But the idea of needing a fast detector, something that can measure something very fast and in optical and radio waves and stuff, that's similar enough.
What kind of detectors do you use to detect those gamma rays from the lightning?
So I don't. So there's an experiment called the RISI satellite, and I don't know the details on it. I know that they've detected what they call TGFs, terrestrial gamma ray flashes, but I don't know what their detector is.
You'll have to forgive this being a non-technical question. I'm a layman. But I saw this fascinating video, what happens when lightning strikes a river? And you have to assume that not everything in the river died as a result of being electrified. What do we know about the dissipation?
So, I don't know how it really dissipates very well, but I can say this. From orbit, we get this global view of lightning, and we can look at where the lightning struck. And when it strikes water, particularly seawater, because with all the salts and everything in there, it's really a good conductor, the strikes are way faster and way more powerful because there's just a huge, you can dump way more charge into such a good conductor. So it's faster. I guess I can say that. It's going to be a faster discharge. It's going to be a more catastrophic thing locally than when it hits the ground. So I would not want to be swimming when lightning strikes,
Also, everyone go home and Google that video, what happens when lightning strikes a river? It's fascinating.
Just two questions there, and they relate to that. I didn't hear you mention, at least, when we talk about, the typical videos that all the news channels carry and everything. What's the current in that main discharge path?
So typically on the order of 5 to 10 kiloamps, but it can get up to 100 kiloamps.
So then the question is, why does it work, or doesn't it, that we use just maybe at the most 9-gauge wire as our ground lightning protection for our rooftop antennas?
I don't know. Maybe every time it does work, you have to replace it. Kind of like a bike helmet. As soon as you use it, replace it.
One distinction we made, because when I was working, we went to remote sites and you would do portable antennas and you would have something kind of permanent. And so we had, one of the best shields we had was one of these things that was kind of these mushroom-shaped, discharge domes, and they worked very, very well. But the distinction, though, is you're trying to divert it and prevent it from striking versus dealing with it when it strikes. So, all the old rooftop spikes and everything, they claim they were diverting it when it strikes, but the current doesn't make sense. That would just blow it out.
I don't know.
So maybe they were doing a better job of diverting.
If it conducts really, really well, it should handle it fine. And otherwise, you might burn it out. I don't know.
Is it rude to ask you about thunder, or is that getting way
No,
over the top?
I don't know anything about thunder.
Oh, okay. Never mind.
Everything I know was the air is superheated and you get a shock and you hear thunder. That's all I hear. Yeah, sorry.
Would it be accurate to say that there was more strikes to the earth of lightning since 2000 than ever before, or just better methods of noticing it?
We certainly are studying it more than we used to, for a number of reasons. So, the whole description of when lightning starts in severe convection, okay? So it's associated with severe weather, right? And if tornado rates increase, and other severe thunderstorm rates increase, then you will have an increase in lightning. But we don't have a long enough record of data to say, oh, look at this increase in lightning. But if severe convective events, hailstorms, thunderstorms, those kinds of things are happening more, then there's more lightning. Also, the team at LANL, our team, deployed sensors, and we saw something in the early 2000s that had not been seen before that's really cool. In hurricanes, it was always thought, so we don't see a lot of lightning over ocean because you don't have a landmass to heat up and get the severe convection. You don't typically get this kind of convection. It doesn't mean never, remember typical, sure you do, but not always. So it was thought that hurricanes, these huge lateral clouds, they're stirring anything that's there, any structure that's there, it's getting all stirred up and it's huge and it's lateral and it's not an upward convection. And so and people don't typically report lightning from hurricanes. With our ground-based sensors, we could see that you do see lightning in hurricanes. Specifically, it traces the eye wall perfectly. You see, like if you map it out, you see a perfect ring in the eye wall of the hurricane of lightning. And every time the hurricane makes a step up in intensity, the lightning rate increases. So it's pretty cool. So it's in any kind of severe weather.
Isn't it kind of like a shear action, that sort
Yeah.
of increases the charge?
Well,
Just like us going across a carpet.
it's not happening in the outer arms very much,
Yeah,
but it's
you have to
happening.
do the eye wall.
Yeah, it's happening in the eye wall, because you don't, this will mix up your charge. You need it to separate, right?
My question is whether or not the perceived precipitation on the ground, snow versus rain versus hail, if there's any difference in the clouds, I guess in the charge, the way it separates, or in the lightning itself and how it occurs. Because people get really excited about thunder snow, but
Yeah.
is it really different, or is it a different type of, I don't know, is there anything different about it?
So if thunder and lightning are happening, you can guarantee that there's, well, almost guaranteed typically, that there's some kind of big convection. And so, so storms that produce a lot of hail, for example, typically also produce a lot of thunder and lightning. Okay, because that hail it starts as graupel and then it keeps picking up more and more ice, and you end up with these huge ice chunks, right? And that's a convective